In our first unit of AP Chemistry, we will be reviewing various concepts learned in your first year chemistry course, including measurement and significant figures. Making observations is fundamental to all sciences, including chemistry. A quantitative observation, also known as a measurement, must include a number and a unit. Scientists recognized a long time ago that a standard system of units had to be established if the measurements were to be useful. We will be learning some different forms of units this year, but some you should be familiar with at this point are mass, length, time, temperature, and volume. Consider the measurement of the volume of liquid using this burette. Notice that the meniscus of the liquid occurs at about 21.9 milliliters. This means that about 21.9 milliliters of liquid has been delivered from the burette into the flask if the initial position of the liquid was 0.0 milliliters. Since we must estimate the last digit, its value may be different if another person makes the same measurement. If we consider these four individuals, we get a result of three different measurements. The first two digits remain the same regardless of who makes the measurement. These are called certain digits. The final digit, which can be different and is estimated, is called the uncertain digit. Let's consider a second example using the burette. Again, the volume is read at the bottom of the curve of the liquid known as the meniscus. In this example, the meniscus occurs at about 20.15 milliliters. No matter who makes a measurement with this tool, the first three digits should be 20.1. These are the certain digits. The final digit is estimated and can be different, and that is our uncertain digit. All measurements have some degree of uncertainty, which brings up the concepts of accuracy and precision. The agreement of a particular value with the true value describes the accuracy. Another way of looking at accuracy is how correct the measurement is. This accuracy depends on the quality of the measuring device being used. Precision, on the other hand, refers to the degree of agreement among several measurements of the same quantity. So it's the reproducibility of measurements and depends on the skill of the person making the measurement. A good example of precision and accuracy is this dartboard. In the first example, letter A, this person is not accurate in their dart throw because they are missing the bullseye, which is the goal, and their darts are all over the board, so they lack precision as well. In example B, although still inaccurate, the darts are all hitting in the same place, so this person has precision with their throwing. And then letter C, a very good dartboard player, is hitting with accuracy on the bullseye and all of the darts are in the same place, so they have precision. Let's consider a couple other examples of uncertainty. In analyzing a sample of polluted water, a chemist measured out 25.00 milliliters of water with a pipette like the one on the right. At another point in the analysis, the chemist used a graduated cylinder to measure 25 milliliters of a solution, like the one on the left. What is the difference between the measurements 25.00 milliliters and 25 milliliters? Even though the two volume measurements appear to be equal, they do convey different information. The quantity 25 means that the volume is between 24 and 26 milliliters, where the quantity 25.00 milliliters means that the volume is between 24.99 and 25.01 milliliters. So in this case, the pipette measures volume with much greater precision than the graduated cylinder. In a second example, to check the accuracy of a graduated cylinder, a student filled the cylinder to the 25 milliliter mark with water from a burette and then recorded the volume delivered. According to the results of his 5 trials, is the graduated cylinder accurate? If we look at the results of his trials with the graduated cylinder, they show very good precision, meaning that he has good technique with the device. However, the average value measured using the burette is slightly different from 25 milliliters. It's off by 1.54 milliliters. Therefore, the graduated cylinder is not very accurate. it produces an error and causes the measurement to be low each time the graduated cylinder is used. Now let's take a moment to review significant figures. When we make measurements, we are going to record all of the certain digits and then one uncertain digit. These numbers are called significant figures of measurement. So for example, with the graduated cylinder on the left, a person may make the measurement of 21 milliliters. However, that would be incorrect. We can definitely see the 21 milliliter mark on the graduated cylinder. So we need to estimate one more digit past what we can see on the tool. So the correct measurement would be 21.3 milliliters, with the 3 being estimated and uncertain. In chemistry, it becomes important to count the number of significant figures in a measurement. So let's review the rules for doing so. Any non-zero integer always counts as a significant figure and was measured on the measuring device. The only gray area has to do with zeros. Leading zeros do not count as significant figures. So for example, 0.0025 only has 2 significant figures, the 2 and the 5. The zeros are placeholders, and if we rewrote this number in scientific notation, we would not need them in the measurement. Captive zeros, which are between non-zero digits, are also always significant. If we measure the 1 on the measuring device and the 8, the zeros had to be measured as well. So this measurement would have 4 significant figures. Trailing zeros at the end of a number are significant only if the number contains a decimal point. So 100 only has 1 significant figure, while 1.00 has 3 significant figures. The other thing to consider when you're doing mathematical operations in chemistry are exact numbers, and they have an infinite number of significant figures. Exact numbers are obtained by counting things like 10 trials or 8 atoms, or they can be definitions where 1 inch is exactly 2.54 centimeters. Now when we're doing mathematical operations, we have to consider significant figures in our answer as well. For multiplication or division, the number of sig figs in the final result should be the same as the least precise measurement used in the calculation. So if we are multiplying these two measurements, 4.56 and 1.4, 1.4 has only 2 significant figures and is the least precise measurement. Therefore, our answer can only have 2 significant figures and would correctly be reported at 6.4. In a second example, we have 1.05 times 10 to the negative third divided by 6.135. This time we are limited by the first measurement with 3 significant figures. Therefore, our answer should also have 3 and would be correctly reported as 1.71 times 10 to the negative fourth. Now you may or may not have learned the rules of addition and subtraction in your first year chemistry course. It's a little bit different. The result has the same number of decimal places, not significant figures, as the least precise measurement used in the calculation. For example, if we were adding these 3 measurements together, we are limited by the second measurement, which is only measured to the 10th place. Therefore, our answer must also be rounded to the 10th place. So our answer should be 44.2. If you were applying the rules of multiplication and division, you would still be limited by that second measurement, but you might think that the answer should be only 44. But again, addition and subtraction, you go by decimal places. Let's look at a second example. If we have 21 minus 13.8, we are limited by the 21, which is measured to the ones place. Therefore, our answer can only be measured to the ones place, and this should be rounded to 7. Since we are doing mathematical operations and rounding, I think it's important for us all to be on the same page as far as the rules of rounding. First, if you're doing multiple calculations in a row, continue to carry the extra digits through until your final answer, then do your rounding. Now when you are rounding, use only the first number to the right of the last significant figure. For example, if the density 4.348 grams per milliliter needs to be rounded to 2 sig figs, you look at the 4, which is right next to the number that needs to be rounded, not the 8. So the correct rounding would be 4.3. If you had looked at the 8, you may have rounded the 5 up, which then would also round the 3 up. So you only look at the first number next to where you need to round. When you're rounding, if the digit you're going to round is less than 5, then the preceding digit is going to stay the same. So 1.33, if we're rounding the first 3, since that is less than 5, we're going to just drop it and stay the same. If the number is equal to or greater than 5, then the preceding digit is increased by 1. So 1.36, we're again rounding the 3. Since the 6 is over 5, we would round up.